In the previous segment, we've seen a demo where we used a pre-trained neural network and RedisAI module for the Redis database to build an end-to-end image recognition system in about a half an hour or less with a fairly small number of lines of code. However, that method only works if your problem can be expressed in exactly the same classes that the pre-existing networks support. And most ImageNet networks, they support 1,000 predefined classes that you cannot change. If that's the case, you could use this method and it will work. But if it's not the case, which is most often, then you need to train a new neural network. Fortunately, there is a very, very efficient way of doing it with both fast in terms of time and computational resources, and also requiring a fairly small number of images to retrain the network. We're talking about a few dozens, maybe a few hundreds. And with that method called transfer learning, you'll be able to still get a state-of-the-art results of very, very good accuracy, a very high accuracy of your classification. And at the end, we will see how we can deploy this neural network for even more efficiency with RedisAI module of the Redis database. So before we go to the workshop part, I'm going to talk about a little bit about the history of large convolutional neural networks and talk about a few types of neural networks that are currently being widely used, and then we will pick one of them as the foundation for our transfer learning implementation. Key ideas that are implemented in the convolutional neural networks actually trace their origins all the way back to the 1960s, when two research scientists, David Hubel and Thorsten Wiesel, conducted a research where they tried to identify which images cause to fire neurons in the brain's cat. And they've been doing experiments for quite some time, for months, and they were unable to get any response at all. So no matter what they've shown the cat, no neurons fired at all. And then one time by accident, they were moving a glass plate with the drawn circle, not the line that's shown on the picture, but the drawn circle on it. And they noticed that one of the neurons fires, and they heard the clicking, audible clicking, because the electrode was connected to basically an audio system that amplified the signal. And when they realized that it's not the dot that was triggering the neuron, it was actually the line, the edge of the glass. And so after that, they started trying all kinds of different types of images, different types of movements, and they build out a lot of research around this area. And one idea they got is that all neurons in the cat's brain and our brain are actually the same. They comprise of the same types of cells. But they're designed in a layered fashion where later cells take the inputs from the previous cells and they use their transform signal to make more and more complex decisions. So when the first cells might recognize an absence of the presence of the light in a certain part of the visual field, then the later cells will be responding to much more complex objects or situations like this the diagonal line moving across the cat's visual field. So these ideas were borrowed into the deep learning neural network designs, and we kind of rebuilt neural networks following this methodology, where we have multiple layers, and as we go down the layers, the concepts processed by these layers become more and more complex. So when the first layers work with the raw data, raw pixel colors or intensities, later pixels respond to much more complex stimuli. And eventually we end up with the very high level classes. And as we saw in a previous segment, that at the end of the day, we can show a pretty complex image neural network, and it will recognize very high level classes such as objects, dogs, seat belts, shoes, cars, and so on and so forth. So specifically, convolutional neural networks use not only this hierarchical model, there are also several key elements that are parts specifically of the convolutional neural networks. And that's convolution, pooling, and the fully connected layer is sort of the same for all types of neural networks. In the third segment of this workshop, we will talk about the details, how these particular elements are designed what the convolution does, how it works together with pooling, and how we go from the image to the final outcome prediction. And in fact, we'll build a neural network from scratch using these elements. But for this part, we'll just use the existing network, and we'll just use these concepts at the high level. So the history of neural networks really starts around late 1990s, when the first fairly performant neural network was built, designed by Jan LeCun and his team, and was used initially by United States Postal Service to recognize handwritten digits and letters. So this is a fairly simple neural network by today's standards, but I've done a lot of work at that time, and this is the neural network that we will build from scratch. And the interesting piece is a part of this neural network is that all the key features that this neural network has are the same features and elements used today, only they're just bigger, there are more layers, but otherwise these concepts kind of remain fairly the same. So that will be a great exercise to learn the details of neural networks. In fact, in PyTorch, this is all it takes to implement LeNet 5. And we'll talk about it in more details shortly. Now, there's not much really what was going on between 1998, because the LeNet was a pretty simple network that could recognize digits, but couldn't really do any more sophisticated processing. Until 2012, when Alex Kruszewski and together with, in collaboration with other researchers, they built a much larger neural network. But the interesting part is AlexNet, which is what the network was called, is extremely similar to LeNet 5 from almost two decades earlier, 15 years earlier, but it's just bigger. It has more layers, it has many more dimensions. LeNet 5 accepts pictures that are size 28 by 28 pixels, so it's a pretty small image, while AlexNet is taking the image that has the sizes of 224 by 224, so it's a much bigger image, and all of these layers are much bigger. So what helped build this neural network is a couple of things. One is, of course, the compute. We got a much faster processors, specifically GPUs became very usable and got a good API to run neural network training on them. And the second thing is you need a lot of data. So again, by that time, because of the internet has been around for quite some time, we got a lot of images, and a lot of them are now labeled. And these images is comprised in a multiple of data sets, and one of them is known as the ImageNet data set that has several million images, all of which are carefully labeled by humans. So now with lots of data and lots of compute, it became possible to train such large networks. And AlexNet kind of started this process, this race to build better, bigger, more performant networks. So once they've shown what a deep neural network can do for image recognition, new designs followed. So VGG16 was one of the following neural networks, and the key element here is that it's a very regular network. It uses essentially the same type of layer again and again, and it's quite a bit deeper neural network than AlexNet. Well, AlexNet has about 10 layers. VGG16, as the number suggests, had already 16 layers. And in fact, the next design had 19 layers. So the neural networks got bigger and deeper, and with that, they were able to achieve better performance. So VGG16 had quite a bit better performance than AlexNet. All of these neural networks, typically, when they have new designs, researchers try to outcompete the previous year's ImageNet competition and post the results if they can. So actually, that year, a different neural network won the competition. The same year, Google designed its network, first called GoogleNet, and later renamed to Inception. So as you can see, it's quite a bit more complex, but in reality, it uses this kind of module comprised of convolutions, kind of the same basic elements, repeated multiple times throughout this network. And what this network was trying to address is that images can have different scale. And so if you can have convolutions of different sizes, the smaller convolution picks up better, finer details in the images, but the bigger convolution can pick up larger objects, respond better to larger objects in the pictures. So how do you know which one to use, smaller or bigger? And here the researchers decided that let's use all of them and let the neural network figure out, how to deal with that and build different weights for different types of images. So as a result, Inception has shown very good performance working with different scales on images. Later, a year later, there was quite a bit of a breakthrough, because as the layers increased, and this is an example of the neural network VGG19, so it's the same type we've seen earlier, but with like slightly more layers. As you can see, there are quite a few layers here. And the main challenge with these networks is that it's very difficult to train them. As you add more layers, and it has nothing with the compute per se, it takes mathematically, when you start propagating the gradient all the way from the end of the network to the weights at the earlier layers, the gradient disappears. It becomes more and more difficult to get updates to the earlier layers. So at some point, if you have enough layers, your early layers will stop training altogether. And so no matter how many times you run the iterations, no matter how long you wait, your network never improves, because it's very hard for these deltas, weight changes, to go through all these layers. And this has been a problem for quite some time. Was a known problem for a while, and different teams were solving it differently, until in 2015 a team of researchers from Microsoft suggested a drastically different idea. So if you think about what a 34-layer network will look like, just taking the same idea and have this a plain 34-layer design. So there's lots of these layers, and the chances are, definitely has been shown, it would be very, very hard to train this network, and it's probably not going to do anything good at all. So what they did is they created these skip connections. So instead of having every single layer talk to the previous layer and nothing else, and so the layer has to pass the entire signal back and forwards, now they have these jumps where the signal can jump over the multiple layers on the way forward and do the same on the way back. In fact, following the skip connections, the signal can travel all the way from the beginning of the network to the end in one sitting without passing through any layers. And what this turned out, that this improves the training tremendously. So now the gradient, the updates can travel back all the way to the early layers much, much faster. And it became possible, in fact, quite straightforward to train much deeper neural networks. If before ResNet having 15 or 20 layers was considered to be a very, very deep neural network, then today ResNet has, in fact, we used a 50-layer network in the first segment, and there are even bigger neural networks that provide an improvement in performance. So this is the network that we're going to use as a actually not this type, only we'll use the one deeper neural network, a 50-layer ResNet, as the base neural network for our training. So, assuming that we're going to use this neural network as the foundation, how can we use it? Actually, how the stressful learning works. The key idea is this: is that as we build a neural network, and it has to follow this layered architecture, simulating what the nature does, right? As we learned in experiments with cats, is that each subsequent layer has more and more sophisticated, deals with more sophisticated concepts. So when you train a classifier, a large neural network, to recognize, let's say, a car and a giraffe, the final output is in fact classes. Is it a car or is it a giraffe? But what actually happens is that in the meantime, different layers learn different concepts about the images in general. So one layer might learn how to deal with basics like dots and lines, and maybe the subsequent layers will learn more about orientation, movements, and further down we'll get more and more complex shapes. And finally, the latest layers will take all this information and combine it together into the final classification. So we will use a pre-trained neural network that has a certain classification, which is typically ImageNet with 1,000 classes, and we'll preserve earlier layers because they have a lot of useful knowledge already embedded there that they learned during the initial training. So we'll freeze the early layers, we'll keep them as is, and we will replace the final layer with our new layer that we're going to retrain for our classes. So in this case, instead of the car and a giraffe, we're gonna leverage all that the neural network learned so far and instead retrain to, let's say, recognize flowers. So in the more specific design of the ResNet 50, we're going to use and freeze all the previous 49 layers of this network and keep them as is. And we're going to remove the final layer, which currently does the classification using the ImageNet categories. And as you saw from the first segment, as 1,000 general purpose categories. And instead, we're going to retrain for our categories. And here you can bring your own data set with any kinds of classifications, 2, 3, 4 classes. And if you don't have your data set, don't worry about it. We will use a data set from Kaggle, which is actually, there is a competition currently running there. So we will use that to train the neural network to recognize completely different classes than the ImageNet. So another insight, in addition to reusing layers, is that when we'll be doing the training of the final layer, the classification, none of these layers, earlier layers, change. So as we'll be passing the image constantly, or different images constantly through the network, training it, the output of this layer next to the last will always be the same. Because when the neural network is trained, it becomes fully deterministic. You pass the image, the same image, you get the same result. So the second optimization that we're going to do, which is they're going to have quite a bit of performance improvement in terms of training, we're going to pass all the images through this first part of the network, the long one, once, save the outputs at this level separately, and these outputs are typically called embeddings. Because the idea is that these outputs now represent the abstract representation of this image. They typically have 1,000, 2,000 dimensions. They're just long vectors of real values. They don't really have any intuitive meaning, but you can think of them as the points embedded into 2,000 dimensional space. So now we converted images into points, and we can work with them as more of a geometrical figures. We're going to save these values, and then we're just going to use these values as inputs to our last layer and train the last layer alone. And because the last layer is a very simple classifier, it's a single layer, essential logistic regression, we're going to train it very, very fast. It will literally take a few seconds. And once it's ready, we will attach this layer to the rest of the network. And now we're going to reassemble, as if from the Lego blocks, the new neural network, leveraging all the previous layers that learned various parts of the concepts of the image, and the final layer that we're trained to recognize what we want, the classes that we need. And after that, it will become a whole neural network, new one, with the classes that we want. Then we can pass a new image into the input, and we'll get the classification at the end. So in the next segment, we will write some code implementing these concepts.